In this video, we're going to begin to learn about moles and solutions. You've probably used counting units all of your life. When we think of pairs of things, we know that that means two, like a pair of shoes. If we have a trio, we know that that means three. If you have a quartet, like a barbershop quartet, it has 4 singers. If you have a 6-pack of something like soft drinks, you would have 6 of those. If you have a dozen eggs or donuts or something like that, you know that that means 12. You may have heard the term a baker's dozen, that means 13. Also a score, which means 12, with 407 years ago, Abraham Lincoln, a score is 20. And a gross is a dozen, or 144. So we just completed the Titan activity. In the Titan activity, your challenge was to figure out how many Cheerios were in a box without counting them. We had limited information about what was in the box of Cheerios. We knew the individual mass of a Cheerio after you did some work, and you know how many the mass of the total box of Cheerios. But in order to figure out exactly what we had, we need to have a counting unit for molecules, and we used the Titan activity to figure that out. So we created a counting unit for convenience. That's called the Titan, because we go to West. And this is a very similar process to what we do for molecules. Molecules are very small. You know that because we've talked about how tiny the individual atom is, and so atoms together are still very small. And so we need a really large counting unit for molecules. The counting unit that we use for molecules is called the mole. It's abbreviated MOL. I know chemists are not terribly creative when it comes to abbreviation, and it comes from the Latin word for mass. The abbreviation, again, is not very helpful, but we can define it in 2 ways. Masses of atoms, and you remember those are measured in AMU, atomic mass units, but we can't actually measure the mass of an atom conveniently. We don't have a balance that gives us a mass in AMU. So we also need masses that we can easily measure, and we measure those in grams. So if we can define the mole in terms of both of those things, it helps us connect the small molecules and the amounts that we can see. So we define a mole in a similar way to the Titan. We define the mole in a similar way to the Titan, and we know that the mass of one atom in AMU is equal to the mass of one atom of a mole in grams. And we know that 1 AMU is equal to 1.66054 times 10 to the negative 27th kilograms. So this should start sounding like what you did in the Titan lab. So what do we need to do now? We need to figure out the connection between the mass of an atom in AMU and the mass of the mole in grams. And we use that to figure out how many atoms are in a mole. So let's look at that. We're going to calculate it the same way as we did in the Titan activity. So from the periodic table, we know that the average mass of one carbon atom is 12.01 AMU. Remember that average atomic mass tells us that. This also means that the mass of 1 mole of carbon atoms must be, by definition, 12.01 grams. So let's see if we can figure out how many carbon atoms are in 12.01 grams. We know the mass of one carbon atom, and we also know the mass of the group, or the mole of carbon atoms. So we need to get the units to agree. Let's start by saying that we know that the mass of one carbon atom is equal to 12.01 AMU. The mass of one mole of carbon atoms, or that group of carbon atoms, is equal to 12.01 grams. So we've got 12.01 AMU, and what we're going to do is we're going to convert to grams. You know what that means. Factor label is back. So 12.01 AMU. We're going to set up our factor. Remember, with factor label, you want to think about the units first. So we know from the previous slide that that 1 AMU is equal to 1.66054 times 10 to the negative 27th kilograms. So we're going to go from AMUs to kilograms first. So we put AMU on the bottom so that it will cancel, and then we're going to go to kilograms on top. So we need to put our conversion on the top there. Our number is 1.66054 times 10 to the negative 27th kilograms in 1 AMU. And then we need to go from kilograms to grams. So again, we want kilograms on top. Kilograms on the bottom. And we want grams on the top so that kilograms will cancel out. Think about where we put our scientific notation. Our scientific notation that goes with kilo, remember, is 1 times 10 to the third. It should go on the top because that is our base unit, grams. And then that's equal to 1 kilogram on the bottom. Use your calculator. Pause the video and punch this into your calculator and see what you get. Okay, now check your answer. You should have gotten 1.994 times 10 to the negative 23rd grams, and that is the mass of 1 carbon atom. Okay, because we said that 1 carbon atom is equal to 12.01 AMU. So we know that the mass of 1 mole of carbon is 12.01 grams. So if we take the mass of 1 mole and divide by the number of grams in each atom, that should tell us how many atoms is in 1 mole of carbon. So we're going to take 12.01 and we're going to divide by 1.994 times 10 to the negative 23rd grams. And that number gives us 6.022 times 10 to the 23rd atoms of carbon. And we can actually do this for any element in the periodic table. If you choose any other element, this will work. You could choose silver, gold, platinum, barium, any of those, and you would get the same number of atoms per mole of material. So let's take a look at how we handle that. So 1 mole is always going to be 6.022 times 10 to the 23rd items. So 1 mole of donuts is 6.022 times 10 to the 23rd donuts. Krispy Kreme would be doing well if we bought that many. A mole of quizzes, I know you think I give that many in a year, but it would be 6.022 times 10 to the 23rd quizzes. A mole of dollar bills, I think by now you know, it's 6.022 times 10 to the 23rd dollar bills. Anything you can think of, 1 mole is 6.022 times 10 to the 23rd. So moles are really huge counting units that we use to tell how many things are in, how many molecules or atoms are in a mole. So let's look at how long it would take us to spend 1 mole of dollar bills. We're going to assume that you could spend $1 million for every second of your life. Okay? So if you have 1 mole of dollar bills, and we know that in 1 mole, we put moles on the bottom and dollar bills on the top. There are 6.022 times 10 to the 23rd dollar bills in 1 mole. And then we could spend $1 million per second, so dollars needs to go on the bottom to cancel out, seconds on top, and that would be $1 million in 1 second. And then we need to go ahead and we need to convert seconds to years. So again, remember, set up your factor, seconds on the bottom, let's go to minutes on top. So 60 seconds in 1 minute. Does this seem like unit 1 again? And then we want to go from minutes to hours. So 60 minutes in 1 hour. And then we want to go from hours to days. 24 hours in 1 day. And then we want to go from days to years. So we have days on the bottom to cancel, years on the top, and we know that there are 365 days in 1 year. And if we include leap year, it's actually 365.25 days in 1 year. So if we calculate that out, and go ahead and pause the video, put this into your calculator, and make sure that you get what you need, and then restart and check your answer, you should get, with 1.91 times 10 to the 10th years, that would give you 19 billion years. So if you were spending $1 million a second, it would take you 19 billion years to spend 1 mole of dollar bills. So we've talked about the fact that moles really are huge, huge counting units. Let's look at some other examples of this. Could 1 mole of basketballs cover the surface of the earth? Yes, to a depth of 50 miles. How big would 1 mole of grapefruits be? If you put them all together into a sphere, they would be about the size of the earth. How many human cells are on earth? So all the 6.5, 7 million people that are on earth, all the human cells on earth, about 1 mole of human cells. And how many moles of sand grains are in the Sahara Desert? About 2 moles of sand grains.